Welcome to the lesson on Newton's universal law of gravitation. Universal law. It's quite a statement. That means it applies to every object in the universe. We don't get to say that very often. Universal law of gravitation in words would be the following: that the gravitational force of attraction between two masses is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. If we were to express those parts individually, we would say that force is directly proportional. One way is to use that symbol. Another way is to express it with that symbol that I just wrote there, the tiddly there. Force is directly proportional to the product of the masses. And over here to the right, we could also say that that gravitational force is directly proportional to the inverse square of the distance between the centers. Now, we're going to take a look at that from a graph standpoint and what that means altogether. So we're going to give ourselves two set of axes underneath each of these equations. On the left one, we're going to put Fg on the y-axis and the products of the masses M1 and M2 on the x-axis. And clearly what this says is, what Newton discovered is that when you graph the gravitational force of attraction against the product of the masses, you get a linear relationship, which indicates that these two quantities are directly proportional to each other. On the right-hand graph, we'll put Fg again on the y-axis, and we'll just put r, the distance between the centers of the objects, on the x-axis. And what he discovered here is that as r increases, the force of gravitational attraction decreases, and it does that in such a manner that a parabola is formed, and this of course indicates an inverse square relationship. Putting both of those together, that would mean that Fg is directly proportional to M1 M2 over r squared. Well, what's the only way that we can get Fg equal to M1 M2 over r squared? Is if we multiply M1 M2 over r squared by a proportionality constant. And a couple major points here is to understand that Newton's universal law of gravitation is an inverse square law, and they love to test this. They love to test this by manipulating variables, which could be anything with mass, either of the masses, and they like to manipulate the distance between the centers and then ask you for the overall impact on the gravitational force. That proportionality constant that we just talked about ended up, of course, being big G, and that value is known as Newton's universal gravitation constant, which has a numerical value of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And if you want to know where those units came from, ask in class tomorrow, and I'll be happy to show you that. And as a result, his overall equation, now we can set Fg equal to M1 M2 over r squared by multiplying M1 M2 over r squared by its proportionality constant, which is big G. Another side note to keep in mind that we reviewed earlier this year was that at the surface of a planet, we have a special application of this, which would also allow us to calculate the acceleration due to gravity at the surface of that planet. What this does, if we consider the force of gravitational attraction between two objects, and one of those objects is the planet and the other object is at the surface of that planet, we have an alternate way to now calculate that object's weight, because the force due to gravity between the planet and the object is the weight of the object. So we set up Fg equals big G, mp, which is mass of planet, times mo, mass of object, divided by the distance between the center of the planet and the object squared, which happens to be the radius of the planet. So we'll throw a little p on there. That's the radius of the planet squared. Well, that is also the same thing as the weight of the object, which we traditionally calculate as the mass of the object times the acceleration due to gravity at the surface of the planet. Well, what we can see here is, since these are equal to each other, that we can cancel the mass of the object, and now we have another way to also calculate the acceleration due to gravity at the surface of the planet by big G, mass of the planet, over radius of the planet squared. If you have any questions on this lesson, make sure you ask in class tomorrow. And the problems that you'll next do use Newton's universal law of gravitation, and then eventually also combine that with our circular motion concepts.